So the first talk is coming from Germany, Darwish from Erlangen, who is going to give the talk. So you're here? Yeah. Good morning. Yeah.
Hi everyone, my name is Elshaimaa. I'm Egyptian studying in Germany, Frederick Alexander University, and I will share with you today a part of my PhD work. My work is about modification of room temperature sensors of lead halide perovskite, and I'm working with this structure. It's a cesium lead bromide, and you can call it zero-dimension cesium lead bromide. So our work is modification. My work is about modification of the sensors at room temperature, and those particles we applied as a downshifting layer in solar cells. And when people hear perovskites and solar cells, they assume it's the active layer that absorbs the light in the solar cell. But in case of my work, it's different. It's just a top layer we placed on top of a commercial solar cells, and it should convert light from UV. From the UV to visible for the solar cell to be able to understand it and absorb it and make use of it. So our sensors approach is a straightforward method at room temperature, and our material here is a material that fulfill the requirements for a downshifting layer, which is absorbing in UV and emitting the light in the visible range. So this is the good news that we had after obtaining the required material, that it has a high Stokes shift. But after we synthesized, according to the published method, we found some problems. Like, for example, we had a very low quantum yield and poor dispersion of the particles, and for the requirement of our application, we need higher quantum yield, and the particles should be well dispersed in the solution, and we also need a small particle size so it wouldn't scatter the light. So in order to overcome these problems, we decided to introduce various modifications to the sensors process. For example, after our modifications, we managed to move the quantum yield from 29% into 55% after combining all the modifications. Our modifications, we had various modifications depending on the step in the reaction. So for example, one kind of modification was the post-synthesis dispersion of the particles. When we add the post-synthesis processing, quantum yield increased to 31%. Another kind of modification is the introduction of tau bromide as injected during the synthesis, and we increased by this modification the quantum yield to 33%. Third kind of modification was just mixing of a polymer inside the precursor solution, and the quantum yield increased to 46%. After we combined all the modification, the final quantum yield increased to 55%. And when we measured the lifetime of the particles, after introducing each kind of modification, we noticed the lifetime was increasing. When we combine the increment in the lifetime and the increment in the quantum yield, we can conclude that each modification has actually decreased the surface traps of the nanoparticles. Afterwards, we measured the XRD of the original unmodified particles here, and we compared it with the XRD spectrum of all of the particle after each kind of modifications, and we conclude that our modification didn't alter the XD structure of the material, which means we maintain the crystal structure. It's just some sort of modification that introduced to the surface of the particle, enhancing the property without changing the structure of the particles. Also, one more thing we noticed, that every time we use a kind of modification, the purity of the product was enhancing. A major problem in the synthesis of the zero-dimension cesium lead bromide is that it always comes with cesium bromide as a side product, which is unrequired, and it's just like decreasing the quality of our product. But each time we were modifying the synthesis or introducing something, we noticed the percentage of cesium lead bromide was decreasing, with the highest decrement in case of introducing the polymer in the precursor solution. We had absolutely no cesium bromide as a side product. We can further explain that with the detailed XRD. Sorry. We can further explain that with a detailed XRD graph. For example, here you can see the XRD spectrum of the unmodified sample, and you can see a very obvious peak corresponding to the cesium bromide impurities appear here. And also a very big obvious peak here, corresponding also to the cesium bromide impurities. If you compare the modified polymer with the reference of the cesium lead bromide, you will find it exactly the same without the impurity peak. One more thing we noticed as a result of our modification to the synthesis process, that we managed to enhance the uniformity of the shape and size of the particles. So the average particle size decreased from 54 nanometer to 39 nanometer, with also the distribution of the size became more uniform. So the majority of the particles have the same size, which is also something that we managed to enhance. After that, we started to characterize the material for its suitability for the application, and for that we did optical stability measurement by making a film of the material and irradiating with the LED light and measuring the emission on different time intervals. In case of the particles without any modification, the emission was decreasing with the passage of time. In case of the particles modified, the emission was maintained almost stable. Also, we measured the water resistance by dropping a drop of water on top of the film, and measures the radius of the water droplet with the passage of time. And here you can see the unmodified particles, that the size of the water droplet increased significantly when compared to the original one, the size of the droplet at zero time, while in the case of the modified particle, the decrement was in a lower rate, which is an indication of the particles, the material hydrophobicity has actually enhanced. And we could correlate that to the polymer hydrophobicity, as the polymer is adding extra water resistance to the material. Eventually, we applied the particle on a top of a commercial silicon solar cell, and here you can see that we measured the EQE of the particles after modification, and you can see the increment of the performance is more significant when compared to the particles without the modification. In case of the modified particles, the increment in EQE was 90%, while 0.9%, while in case of the unmodified particles is only 0.2% percentage. So as a conclusion, we can, to sum up, we enhanced the colloidal synthesis of the cesium lead bromide at room temperature. The SEM showed more uniform size and shape. XRD has showed better purity of the obtained particles, and the application on top of a commercial solar cell has enhanced the performance in case of the modified particles when compared to the unmodified particles. At the end, I would like to thank the DFG and the DAD and my graduate school for supporting me during my PhD. And also, I would like to share with you the link to the published paper, the link to ResearchGate, and the link to my LinkedIn profile, because we're all here to network. I would be honored to connect with you later on.
Thank you very much. we have, so